Algebra 2 students, let's start our last Algebra 2 unit, and it has everything to do with the following. Take a right triangle. Call this theta. And the sine, cosine, and tangent of theta is the relationships between the opposite, adjacent, and hypotenuse. So if you take your standard 3, 4, 5 triangle, we know that the sine of theta equals 3 over 5. That also means there exists a triangle similar to the one I just drew, where the hypotenuse is 1, and the opposite side, this is theta, the same angle as this, and the opposite side is 3/5, and the adjacent side is 4/5. And what's interesting about this is we can actually say that the opposite side is actually the sine of theta. It equals that. The sine of theta is 3/5. Well, look, this side's 3/5. We can also say that the adjacent side is the cosine of theta. Over here, the cosine of theta would be 4 over 5, and look, there it is, 4 over 5. Cosine of theta would be this divided by 1, or just the adjacent side of a triangle whose hypotenuse is 1. Now in Algebra 2, we take this special triangle that has a hypotenuse of 1, and we set it in the coordinate plane, so it looks like this. I've got my xy axis. Here, hold on, let me start over. Trick on drawing the perfect circle in a coordinate plane. Draw the circle first, then draw the axes in the middle. So in Algebra 2, we take a circle of radius 1, and we call it the unit circle. The reason it's called the unit circle is because the radius is 1 unit. Inside this circle, we can set any right triangle we want by creating this right here, where we have theta right here. We know the radius is 1, and this point right here is some x comma y point, and we know it's on the circle. And looking at the circle, we can see that this adjacent side of the triangle is x, and we can see that this opposite side of the triangle is y. Now, from Algebra 2, or in Algebra 2, we will talk about angles starting right here and wrapping around the circle. So an angle of 0 degrees starts on this side of the x-axis, and its terminal side is right here. So that's a 0 degree angle. It's just a ray. And an angle of 90 degrees ends here, and an angle of 180 degrees ends here, and an angle of 270 degrees ends here, and an angle of 360 wraps all the way around once and lands back here. And you can have any angle measure between 0 and 360, and it will land somewhere on this circle. 120 lands up here. 225 lands right there. 330 lands right here. And then you can have angles that are bigger than 360 that also wrap around and hit somewhere. So you can have an angle of 420 degrees, and it hits right up here. 420 degrees goes around the circle once, that's 360, and then 60 more. So what we're going to do is I'm going to walk around some pretty special angles around the unit circle. So I'm just going to draw a circle, and I'm going to walk around some special angles that you already know about because you've been a good geometry student. So here's my XY plane, and I'm just going to start with 0 degrees, and I'm going to go around adding 30. And I'm just walking 30-degree angles around the circle, hitting in these spots where they would hit, right? 210, 240, 270, 300, and then 330. Not to scale. For each angle that is with a 30 degree here, I'm going to show you how this angle here is 30 degrees. I'm going to draw this angle right here. This is 150. It goes all the way around the circle to this point right here. That's 150 degrees. So what's this angle right here? It's 30. I'm going to draw the angle to 210. Do you see how that's 180 plus 30 degrees? 330. Do you see how this right here is 30 degrees? Notice that those four angles all make a 30 degree angle with the x-axis. That means I could draw a triangle here where every single one of those triangles, sorry this is not to scale, every single one of those triangles though has a hypotenuse of 1 and is a 30, 60, 90 triangle. I wonder if we know how to find the sides of a 30, 60, 90 triangle if we know the length of one of the sides. Curious. Now I'll look at all the angles here with 60 degrees. Notice it also creates a right triangle here where this angle is 60 degrees. Look at 120. Notice that the angle with the x-axis would be 60 degrees. Look at the same with 240, not drawn to scale. This right here would be 60 degrees. And then the last one, 300. Notice that this angle right here would be 60 degrees. And now I have a similar right triangle, actually a congruent right triangle, where I have a 30, 60, 90, and I know the length of the hypotenuse. I wonder if I could find the other two sides. Curious, curious, curious. Let's look at some other special angles. This time I'm not going to walk 30 degrees around, I'm going to walk 45 degrees around. So here's 0, here's 45, 90, 135, 180, 225, 270, 315, and 360. Notice those triangles also, notice that those angles also make triangles with the x-axis, such that the angle between the terminal side of the angle and the x-axis will always be 45 degrees. And now what I have is I have a bunch of 45, 45, 90 triangles. Good? Now, why does this matter at all? Well, if you remember from geometry what you're supposed to know, that for any 30, 60, 90 triangle, if you know the hypotenuse and you know this is 30 degrees, the side opposite the 30 degrees is half the hypotenuse. The side opposite the 60 degrees is the square root of 3 times the side opposite the 30. If you have the other triangle where you know this is 60 degrees, and this is 1. Well, you know the side opposite the 30 degrees is 1/2 the hypotenuse, which in this case is 1/2, and the side opposite the 60 is the square root of 3 times the side opposite the 30. And then lastly, if we look at the 45, 45, 90 triangle, this one you want to be careful with, because if you know the hypotenuse is 1, then you know each side here is the hypotenuse divided by the square root of 2, which we want to rationalize by multiplying by root 2 over root 2. And here we get root 2 divided by 2 and root 2 over 2. Good? What's the point of all this? I got sick of drawing inaccurate unit circles, so I have one here. The point is if we know all of those relationships about the unit circle, I can take this angle here, which I know is 30 degrees, and I know because this hypotenuse is 1, I actually know that the x-coordinate is the cosine of 30 degrees, and I know that the y-coordinate is the sine of 30 degrees. And now without a calculator, I can think about the x-coordinate, which should be root 3 over 2, and the y-coordinate as 1/2, and I now know the sign of I now know the value of cosine of 30 degrees just by looking at the x-coordinate here. I know it's root 3 over 2. I can use this unit circle to visualize how that's the longer of the two segments. I can then also look at this 45, 45, 90 triangle here associated with the gold at 45, and I can see that the sine and cosine of 45 are the same, and they're root 2 over 2 and root 2 over 2. I can then use a third color here to look at 60 degrees and visualize that at 60 degrees, the x-coordinate is shorter, so it's the 1/2, and the y-coordinate is bigger, so it's root 3 over 2. I can also then, in black, look at this at 0 and see, well, if the x-coordinate here is 1 and the y-coordinate is 0, then that must mean the cosine of 0 is 1 and the sine of 0 is 0. Similarly, up here at 90 degrees, I can see that the cosine is 0 and the sine is 1. So the unit circle helps us visualize from this definition that the x is equal to the cosine of theta and y is equal to the sine of theta. Knowing that, we can actually visualize the values of cosine and sine for all sorts of special angles. In using what we know about the coordinate plane and similar triangles, over here all we have to do is take care of positive and negative signs when we move around the coordinate plane. So I know that the cosine of 135 is negative root 2 over 2. And I know that the cosine of 150 is negative root 3 over 2, but the sine of 150 is positive 1/2. And I actually know that the cosine of 180 degrees is negative 1, and the sine of 180 degrees is 0. And I can walk around all of the unit circle just putting these congruent triangles in here at where they would be with 30, 60, 90 triangles or 45, 45, 90 triangles. And I can easily say, oh my gosh, look how easy it is to find the exact values of different special angles when I'm using trig functions. I no longer need a calculator to talk about what the exact value of the cosine in this case is 240 degrees. It's negative 1/2. Not only that, you've got this special thing that I didn't even mention. You can now take the sine and cosine of any angle in the world, not just acute angles. Before, we only knew them as acute angles in right triangles. Now I can see that they exist because there's a right triangle for any one of these. So this is called the unit circle. It's something that I want you to memorize, but more than memorizing it, I want you to understand where it came from. Did you notice that I didn't just say memorize these values with no context? I tried to show you that all of these exist because of the special angles that we already know and the special triangles we already know how to deal with. Sorry about that. And I can't erase with this, unfortunately. I wish I could. So here, let me just cross this out. This is negative root 3 over 2. So what I want you to work on tonight is memorizing this unit circle. For now, I do not want you to think too carefully about other types of angles, because we'll get into how do you measure these angles in different ways. Right now, I really want you to understand the degree measure of all these angles and where they come from. The 45 plus 40, 0 plus 45, 45 plus 45, 90 plus 45, 135 plus 45, 180 plus 45, 225 plus 45, 270 plus 45, 315 plus 45. And then again with 30. Let's do it, in a red marker. We can actually do it with 60. We'll do 30. 0 plus 30, 30 plus 30, 60 plus 30, 90 plus 30, 120 plus 30, 150 plus 30, 180 plus 30, 210 plus 30, 240 plus 30, 270 plus 30, 300 plus 30, 330 plus 30. And everything bigger than 360 we can just map to here. Now there are angles, and you can look this up on your calculator. If you take the sine of 50 degrees, 50 lands between 45 and 60. It lands about right here. And I promise you that the cosine of 50 degrees is a little bit bigger than 1/2 and a little bit smaller than root 2 over 2. And I'll tell you that the sine of 50 degrees is a little bit bigger than root 2 over 2 and a little bit smaller than root 3 over 2. Because we don't have a special relationship with 50, 40, 90 triangles, I can't find an exact value of that sine and cosine without a calculator, but I can estimate it. Because of 30, 45, and 60, because they have those special right triangles, that's what allows me to find these different points. So your homework tonight is to memorize this, but not just memorize it, understand it. Know why it's a positive 1/2 here and a negative root 3 over 2. And that's just because if I draw this 30, 60, 90 triangle that hits here, I would have a hypotenuse right here of 1. I would have a 60-degree angle here with the x-axis. That would mean this side right here, this x-coordinate is 1/2, and this y-coordinate is negative root 3 over 2. Negative because it goes down, positive because it goes over to the right. If I was to draw the right triangle right here, I would have an angle right here of 30 degrees. That would mean this adjacent leg is root 3 over 2, but it would be negative because it's going in the negative x direction, and the y-coordinate would be positive 1/2. If I had this 225-degree angle here, I would have a hypotenuse of 1, a 45-degree angle with the x-axis. That would make this a 45-45 right triangle. That would make this adjacent leg here negative root 2 over 2. Negative because it goes backwards, and this would be negative root 2 over 2. Negative because it goes down. This is a huge moment in your mathematical career. You now know that you can take the sine, cosine, and tangent. We'll do that later. But you can take the cosine or sine of any special angle or any multiple of a special angle between 0 and 360 by using the right triangle that you already know that are special from geometry. This unit circle becomes a very useful tool in evaluating the sine, cosine of those special angles. All right, a little rambly today, but I hope you get it. Have a good night. Peace.